So let's move to the last unit, which is the control of gaseous pollutants. So we've looked at a number of different control strategies, from absorption, adsorption. We've looked at concentration, using condensers, and the last unit that we'll look at is incineration and NOx reduction. So oxidation systems are often used to destroy organic chemicals that are classified as volatile organic chemicals and or air toxins. Oxidation typically is rapid and requires only oxygen and heat. Now, earlier in the semester, we looked at oxidation of organics. We focused on the conversion of these organics to CO2 and water. So we talked about that as perfect combustion. However, combustion is not perfect, and there are numerous byproducts of incomplete combustion, and these include dioxin, which looks like this. Basically, it's a 6-ring structure with 2 oxygens and 2 unsaturated bonds. Dioxin is considered one of the most toxic chemicals, and it has been one of the major concerns of exhaust from incineration. Another problem that we need to consider if we're using any sort of incineration or oxidation process is, for instance, the conversion of both sulfur and hydrogen sulfide to SO2. And we've talked a lot about SO2. We've looked at SO2 emission. We also need to consider the conversion of nitrogen-containing substances to NO and NO2. Another problem is chlorine, which can leave as hydrochloric acid. We can have heavy metals in the emissions, and in fact, the previous administration strengthened the regulations for mercury emissions from coal-fired power plants, and it looks like that will be weakened. It's really interesting. It's hard to know what exactly will happen there. Many of the industries have put in their treatment processes. They're extremely expensive to put in. So in some respects, I think that industry will actually take the lead in this case, and we'll see these processes remain online and hopefully continue to reduce mercury and other heavy metal emissions. Now, direct flame incineration is often the method of choice so this is really, it's the method of choice where the gas stream has a sufficient heat content so that you can avoid the need for supplemental fuels. If you need supplemental fuels, then that gets much more expensive. And then you also have potential emissions from those supplemental fuels. And just to kind of give you a comparison, I've got this in terms of BTUs per cubic feet. So natural gas is about 1,030 BTUs per cubic feet. Methane is 1,000 BTUs per cubic feet, and landfill gas is about 500. And the reason landfill gas is about 500, it's roughly half of methane is because that landfill gas typically contains 50% methane and 50% CO2. Efficiency of these direct flame incineration systems can be greater than 98%. It's good efficiency. Whether that is sufficient really depends on your regulations. And it's been used for a number of industries, from varnish cooking to meat smokehouses, and I just realized I have this on there twice. Meat smokehouses, just to give you an idea of the type of emissions, it's everything from particulates to carbon monoxide, various VOCs, various polycyclic aromatic hydrocarbons. There are organic acids, NOx. So a significant variety of compounds that need to be dealt with. Your paint, bake oven emissions, these are predominantly the volatile organics. This is just an image of the schematic of a direct flame incinerator. These are very simple. They typically include only a combustion chamber, which you see. Okay, so you've got fuel, you've got your gas stream that you're treating, and any additional makeup air is treated, and you're combusting that in some sort of a chamber, and those hot gases then can be released. Now, with thermal incinerators, or also referred to as thermal oxidizers, here the combustible gas passes over or around a burner flame and into a residence chamber. And I've got a diagram here, just we'll go back and forth, but what you see is that you have air, fuel, your contaminated stream, and this is heated in a combustion chamber. You've got turbulent mixing there because you want significant mixing. That heated gas then moves into a reaction chamber where what you're attempting to do is to react these organics and combust them to ideally produce CO2 and water. In order for these to operate properly, then we need a constant concentration of the combustible gas. So we need some sort of a combustible gas. We need a constant flow rate of these gases. And the efficiency is going to depend on the improper mixing of the vapor and our combustible gas and specific residence time. And typically, when we're looking at these processes, we talk about the 3 T's, and that is temperature, time, and turbulence. So typically we're running these at about 1600 degrees Fahrenheit. Our residence times vary about a second, so they're not very long. And with that, we can ensure about 98% destruction of most compounds. A little bit longer, we can get up to 99%. That detention time varies significantly depending on the type of waste that you're actually combusting. If you're looking at, for instance, a hazardous waste, you're typically talking at least a second. If you're talking about biomedical gases from a biomedical operation, then you're talking at least 2 seconds. The design temperatures, residence times typically are determined from pilot studies. They also will use experimental data from the literature and the regulatory limits. Now, This is just another example of a thermal incinerator or thermal oxidizer. In this case, we have a heat exchanger. So in this case, what we're attempting to do is to recover some of that heat from the effluent gases. So if we can recover a portion of that sensible heat from the combustion process and then recycle that, we can reduce the amount of fuel that's required. Main disadvantage of this is that we need to minimize particulate matter. The particulate matter can foul the surfaces of the heat exchanger tubes. That reduces thermal efficiency of heat transfer, which is exactly what we're trying to do with this, what's referred to as a recuperative heat exchanger. Now I'm going to do a simple example looking at determining the volume of a reaction chamber. This is a very simple approach. In reality, we would need to look at and include the flow rate of the fuel that we're combusting, any additional air that we would need to add. We would do a mass balance around the energy, and that would determine our flow rates, and then we would use those flow rates in determining the detention time in our combustion system. But for simplicity, we're just going to look at this as a very simple system. We have an incinerator. We're looking at destroying cyclohexane. We have a waste stream that is 4,000 cubic meters per minute. And I didn't change this. I changed it to 1-dioxide. I apologize. I'll fix this in the notes later. And we need to remove, and this should be not cyclohexane, this should be dioxane. We need to remove this 1,4-dioxane at an efficiency of 99.95%. And we have a rate constant of 3.8 inverse seconds. So we have a first order reaction. And what we want to do is determine the volume of the reaction chamber. So let's insert a new slide. Okay. So what do we know? Okay, we have a flow of 400 cubic meters per minute. We need 99.95% removal. We have a temperature of 1,000 degrees C. We have a rate constant of 3.8 inverse seconds. 1,000 degrees C is used in some incinerators. These are high temperature incinerators. There are actually none known in the state of Michigan. That's actually been one of the major challenges with the PFAS chemicals, which you may or may not have heard of. These are contaminating a significant number of water supplies, and in many cases, activated carbon is being used to remove the PFAS chemicals from these water supplies. Problem is, we put it on activated carbon. Now what do we do with the activated carbon? And if we can't treat that activated carbon by normal regeneration processes, because that would just emit the PFAS chemicals into the atmosphere. So what is typically done is to incinerate that spent activated carbon. The problem is to incinerate it, we need a high temperature incinerator. So we're talking about 1,000 degrees C. So yes, these do exist. Now, typically, we will model these combustion processes as a plug flow system. Okay? So our efficiency, we said, was 99.95%. 5%, okay, which means that, so this is our efficiency, 99%. That means we're going to write this as a effluent. That means take 1 minus our efficiency. We have 0.05% of the initial concentration in our effluent gas stream. Okay. So C over C naught is equal to 0.0005. And if we have a plug-fed system, we can model this as the natural log of C over C naught is equal to minus KT. And this is ln C over C naught is 0.0005. Or we could have written this as 1 minus 99.95. Could write it either way. And that is equal to minus 3.8 inverse seconds times T. And if we solve this, T is equal to 2.0 seconds. So we would need a detention time of 2.8 seconds. You're given the flow rate, and the volume is equal to Q times G, which we've looked at before. So if we multiply that volume that was given by 2.0 seconds, we would need a reactor that would be about 13.3 cubic meters. Now, remember, this is a very simple approach. As I've mentioned, in reality, what we would need to do is we've only looked at our contaminant gas stream. We would also have to determine the flow of our fuel, and if we need air. We would need to include the total flow rate, and we would determine that, as I mentioned before, by doing an energy balance on the system. But we won't do that today. So we're really just looking at a number of these processes. Catalytic incineration is very similar to thermal incineration. The major difference is that a catalyst is used to, one, lower the temperature of the incineration process, and that reduces fuel consumption. And we may be able to increase the rate of reaction, which decreases the size of these units. So basically, it's an incinerator, large boiler system, no different than before. The big difference here is what we would do here is we put in some sort of a catalyst. Okay, so we've set some sort of a catalytic material inside this reactor to improve the rate of oxidation and, again, to lower the temperature. These are best suited for when there are low VOC concentrations and low particulate matter. And the reason for the low particulate matter is that if particles settle on this catalyst, they deposit on the surface, and that's referred to as fouling. And that fouling decreases the efficiency of the catalyst, And unfortunately, these catalysts are often very expensive. In most cases, for instance, most metal oxide catalysts are poisoned by chlorinated VOCs. So for instance, thinking back, we mentioned that groundwater that's contaminated with tetrachloroethylene or trichloroethylene. You then have removed that, let's say by an adsorption process, and then you're looking at regenerating that adsorbent so you have this perk in your off gas. So you just want to treat that off gas so you're not discharging perk, in which case the problem there is, okay, I can use incineration, but if I look at catalytic incineration, I have to make sure that I have a catalyst that isn't going to be poisoned by that chlorinated compound. And many of your platinum, for instance, the platinum-based catalysts are poisoned by the presence of chlorine and fluorine. So the choice of these catalysts can be a bit challenging. You're really working typically with a supplier to make sure that that catalyst is the optimal one for the situation at hand. And this just shows you a cutaway of a catalytic oxidizer, and you can see you've got these catalysts that are lining the inside of this reaction chamber. And as I mentioned, the major advantage here is that you're reducing the temperature. You can potentially reduce the size of the unit, but you really have to consider the effect of the contaminant stream on both physical and chemical deterioration of the catalyst. Now, in the US, more than 10 million tons of NOx is emitted to the environment each year as a result of burning fossil fuels. We've talked about ozone formation in the troposphere, photochemical smog, and we've learned that controlling NOx is critical to controlling ozone formation and photochemical smog. Therefore, important in protecting the public health of the public. The controls on NOx have been primarily on combustion system modification. So we need to look a little bit at how NOx is formed in the atmosphere. There's really three mechanisms. The first mechanism is thermal formation. So air contains nitrogen and oxygen. And at high temperature, these can react to form NO and NO2. Now, this reaction here is shown as reversible. It is a reversible reaction, but the reverse reaction is extremely slow. So basically, once you form NO, it's unlikely that to any extent that NO will reform into nitrogen and oxygen gases. That NO can also react with oxygen to form NO2, but typically in a boiler or any sort of combustion device that we're talking about, the length of time that those gases are present in the incinerator, in the boiler, are too short for NO2 concentrations to build up. So really the most important of these two compounds is NO, and the formations are affected by temperature, by time. So let's same as temperature, time, and also the amount of oxygen present, because we need oxygen in order for these reactions to occur. So we can reduce these reactions by reducing the amount of oxygen present. Actually, in the maximum temperature zone, we can reduce the flame temperature, and we can reduce the residence time at the peak temperature. So typically, if we're looking at reducing thermal formation of NOx, these are the modes by which we can accomplish that. Now we also can form NOx from the fuels that we use. Typically, coal and heavy oil contain somewhere between 0.5 to greater than 2% nitrogen. Okay. So we have nitrogen in these fossil fuels, and that nitrogen can also react in this incineration process, in this combustion unit, to form NO and NO, predominantly NO, but also NO2. And that's going to depend on the amount of nitrogen present in the fuel, the amount of nitrogen present overall. Challenges are that the relationship is not linear. And it's quite complex. So it's difficult to predict, knowing how much nitrogen we have in the fuel, how much NOx we will produce. And also the mixing rate of the fuel and the air. So we're back to turbulence. So there's 3 T's, remember: time, temperature, and turbulence. Again, we can reduce the amount of, in this case, fuel NOx by reducing the amount of nitrogen in the fuel. So for instance, when we've switched from coal to natural gas has much less nitrogen than coal, so that reduces the amount of nitrogen in the fuel, reduces our fuel NOx production. We can also look at a variety of different processes. We can reduce the amount of excess air firing. We'll talk a little bit more about this because we can relate this back to some work that we did earlier in the semester. There's various different designs for boilers to reduce NOx formation. We can look at staged combustion. So for instance, stage 1 is a fuel-rich, low net oxygen mode. And then stage 2 is operated at an air-rich mode. So by trying to use the staged combustion process, we can reduce NOx. And then we can use a high air preheat. So we're preheating the air. This is rarely used in large boilers simply because of the energy consumption used in heating that air. And the last of the 3 is referred to as prompt NOx formation. And here what we have is we have free radicals that are formed in the burner flame. So this is in the flame itself. These can be cyanide, hydrogen cyanide radicals. These can be NH. They can be nitrogen radicals. These react to form NOx. challenge with these is that typically your free radical reactions are not affected by temperature. So you're not going to see that we said effective temperature. Temperature doesn't play a significant role here. And the other thing is that combustion modifications really have very little influence on this prompt NOx formation. We're really focusing on the thermal formation and fuel NOx. The one modification that we'll look at a little bit in more detail is low excess oxygen. So if you think back to earlier in the semester, we looked at various stoichiometric reactions where we had, for instance, carbon reacting with oxygen to form CO2. We had hydrogen reacting with oxygen to produce water, so we had a perfect combustion process. We also looked at sulfur reacting with oxygen to form SO2. And we calculated the concentrations of gas streams. And what we used was excess air. So we wanted to ensure that we had sufficient amount of oxygen. So when we did these calculations, we used typically around 50% excess oxygen. 50% is on the high end, typically for coal-fired boilers. You're looking about 20 to 50% excess. Down to natural gas, and just to give you an idea, we're looking at only about 3 to 5% excess. But we made these calculations, and let's just, if I remember right, we used 50%. Now, if we can reduce that and from about 50%, then we should get somewhere around a 15% reduction in the total flow rate that we need. This is going to reduce heat loss. It improves our efficiency. Okay. But we need to be very, very careful. What you can see from this graph here is we're plotting NOx, actually, sorry. We're plotting concentration, in this case of carbon monoxide and organics. So we've got partially burned hydrocarbons. So what do we see? There's essentially the sweet spot. If we reduce the concentration of oxygen too much, then we increase our carbon monoxide concentration, we increase our hydrocarbon concentrations. We also typically increase particulate matter concentrations. So we've got to be careful not to reduce that oxygen and too low, because if we do, as I mentioned, then you have other problems with both carbon monoxide formation, hydrocarbon formation, particulate matter release, and then the last problem is that particulate matter can actually cause fouling on your boiler tube surfaces. So and that decreases the efficiency. So we can use low excess air combustion, but we have to be very careful in the operation of that. The other thing we can do to reduce NOx emissions is recognizing that typically the problem of ozone levels in the troposphere are seasonal. So we may not want to make, or may not be cost effective to make significant changes in your boiler system, because you may only need to reduce the NOx levels at particular during your high ozone seasons. And when MSU was burning coal, they did use this selective reduction treatment. And what is done is that you add a small amount of ammonia or urea, and that reacts with the NOx. So this is urea, and we have ammonia that can react with the NOx that's formed, predominantly NO that's formed, and that will produce N2, and H2O, okay? And potentially carbon dioxide, okay? So what you're doing is you're reducing the NO to N2 in the boiler itself. So they actually inject the urea or the ammonia into the boiler. That can achieve up to 60% reductions in NOx. But the big challenge is that if you're not careful, either if the temperature is too low or if you have improper mixing, then you get what's referred to as ammonia slip, and then you're releasing ammonia in the atmosphere. Temperature's too high, then you have additional NOx emissions. So you've got to balance that temperature, balance the amount of ammonia or urea that's actually injected into the boiler. The real advantage with this is it's simple, it's compact, and concentrations and additions can be done on a seasonal basis. And that's exactly what MSU did when they were still burning coal. The last thing we'll look at are mobile sources. So everything we've talked about to this point are stationary sources. So how can we reduce emissions, specifically of NOx from mobile sources? And the major way that has been done is three-way catalysts. So basically what these work, so that they're oxidizing NOx, reducing NOx to nitrogen and oxygen. They oxidize carbon monoxide to CO2, and then the unburned hydrocarbons react with oxygen to produce CO2 and water. So assuming perfect combustion there. Okay. So these are active catalytic materials. Platinum is one, palladium is another. Typically they have a oxide-based inorganic promoter. These are free radicals reactions that are generated, and they have a support media. So basically what happens is the exhaust fumes from the engine pass through a catalytic converter. Typically there's an oxygen sensor and a computer to control this process, and that converts the carbon monoxide and the unburned hydrocarbons to CO2 and water, and then reduces NOx to nitrogen and oxygen. In addition, we typically now install particulate filters to trap particulates in exhaust. This is especially important for diesel exhausts. You can control carbon monoxide. You can control your NOx emissions by switching from a gasoline-powered engine to a diesel. However, the real problem with diesel engines are particulate matter. We now have also been installing vapor recovery systems, and these capture the gasoline vapors before they escape from both the hot engine and from the fuel tanks. It used to be, and sometimes still, car is stopped at a red light, surges forward when the light turns green, and you smell this hydrocarbon, typical hydrocarbon smell. That used to be much more common than it is today. You can often see that that black actually soot coming from the tailpipe, from the particulate matter that was being emitted, and that smell, typically a white fume, unburned hydrocarbons. And we're doing a much better job at capturing that material, reburning it, and reducing emissions. The other alternatives are switching to electric cars or hybrid vehicles. The electric car is often sold as zero emissions, which is somewhat a misnomer. Electricity is produced. Emissions come from the power plant, unless it's a nuclear power plant, and then we've got other issues. But we typically have emissions from these power plants. We have a smokestack, and so there are emissions from an electric vehicle. It's just they're from a stationary source, which typically are easier to control than these thousands of tailpipes from various vehicles. The other thing that we have done is to reformulate gasoline, and I should have changed this, it's 25. Now, roughly 25 states and District of Columbia require cities with the worst smog pollution to use some sort of a reformulated gasoline. The idea is that this gasoline contains less volatile organics, so there's less of these organics being emitted, even during pumping of gasoline. Oxygen additives are used to make the gasoline burn more efficiency, and then often detergents are added to try and prevent buildup of engine deposits, keep engines running smoothly and more efficiently. So the other thing that was done back in the 1990s, starting in there, methyl tertiary butyl ether, MTBE, as commonly known, was added as a oxygen additive to gasoline. This increased octane numbers, was used as an anti-knocking agent. It was used in part to replace lead, which was also added to gasoline as an anti-knocking agent. The real problem is it is miscible in water. It is highly soluble and it is toxic. The problem is if you have a leaking underground storage tank that contains gasoline that has MTBE added, that MTBE moves with the waterfront. So it moves with the waterfront, it's soluble, so you can obtain high concentrations of MTBE in the groundwater. It also helps to solubilize benzene, toluene, ethylbenzene, compounds which are carcinogenic or potentially carcinogenic. So it was added for a number of years until it became very evident that we had this significant problem, and at which point it was banned in at least 25 states in the US. And lastly, ethanol is also being used to reformulate gasoline for the exact same reasons that are mentioned above. Again, it's added to increase the octane number and as an anti-knocking agent. The irony was in the 1920s, ethanol was actually discovered as an anti-knocking agent. It was discovered before tetraethyl lead was discovered to be an anti-knocking agent, but the petroleum industry, the auto industry chose not to add ethanol at that point in time and search for others because they didn't want, particularly farmers, but they didn't want ethanol to be produced. They couldn't patent ethanol production, and they thought that that would have potentially a significant impact on the petroleum industry, the gasoline industry. So they kept searching until they found tetraethyl lead, and we all know the tetraethyl lead story. The last thing that is often done, it's really not a control mechanism, but it's essentially a check on these control systems. In a number of states, as part of the state implementation plans we talked about earlier, the states have mandated vehicle inspection and maintenance programs. So basically, when I lived in New Jersey, on a yearly basis, you had to bring your car to a state inspection station. They monitor the car for a number of reasons, structural integrity, down to emission controls. And depending on whether or not you met the requirements, you either passed inspection and you got a green sticker for your car, or you didn't, and in which case you had to fix it and then come back through the inspection station again. So these are often used, especially in designated urban areas, again, to try and meet these SIPs. They're not really a control strategy in that they're not changing the operation of the car, but they're ensuring that the car is operating properly. So I will end there. And we've gone through a number of air pollution control devices. Hopefully I've kind of brought things back in terms of the rest of the semester and how this all connects together. And that helps you to understand how we develop strategies and design systems to ensure compliance with all of these federal and state regulations. So we'll end there. If you have any questions, let me know. Otherwise, as I mentioned, we will meet on Wednesday, and I'm actually having some fun planning this. So hopefully you'll all attend on Wednesday. Tell your teammates that we're gonna have some fun on Wednesday. If you want, bring a cup of coffee, bring whatever you wish to drink. I won't tell you either way. And we will celebrate the end of the semester. And those of you in civil, chemical, and environmental engineering that are graduating. So I will end here unless there's questions.
Hi, Professor.
Yes.
I checked the syllabus on the DTL, so we don't have the final exam, right?
There is no final exam.
So we just need to finish the project, right?
That is correct. You finish the homework, which is due on Friday, finish the proposal and your poster. Normally we would have a poster presentation, but because of COVID, we won't have the poster presentations. You'll just upload the PDF of your poster.
All right, thank you.
No problem, thank you. Any other questions?